Okay, we are going over Fourier series. So period is 2L. If f of x is a periodic function and it is a period of 2L, so this L number is half of whatever the period is, then you can rewrite it in the form of a Fourier series. And then there are these crazy integrals that I'm writing down, which is how you figure out the numbers in front of the cosines and sines, and also this constant. And so the numbers in front of the cosines are 1 over L integral from minus L to L f of x times the cosines. And the numbers in front of the sines are 1 over L integral from minus L to L f of x times the sine thingies. Okay, cool. So are you guys all familiar with these formulas as they're written? So basically the work of doing a Fourier series problem is just like whatever your function is, plug it into these integrals and do them. Okay, so now there's some special cases, right? Like this simplifies a whole bunch if your function is either even or odd, right? And that's where we get this notion of a half range extension, basically. We just sort of like assume the function's even or odd. So special cases, I can spell special cases, if f of x is even, we can simplify the formulas for a naught, an, and bn quite a bit. So if f of x is even, what can we do to simplify, say, like a naught?
You could double it and go from 0 to L.
Yeah. So the a naught would be, instead of 1 over 2L, it would be 1 over L, 0 to L, f of x dx. And then what about an?
It's 0.
So let's see here. So if f of x, so cosine is the even function out of these.
Okay. Because isn't it even times even is odd?
So let's see how that works. So let's see here. So the way I like to think about it is because, so like x squared is an even function, right? And like x, so if you have x to an even power, that's an even function. And if you have x to an odd power, that's an odd function.
Yeah.
So like x squared is even, x cubed is odd. So if you take like an even times an even, so if I take like, so even times even, so an example of that would be like x squared times x to the fourth, say. What do you get when you multiply those two things? Oh, that's an x there. Let's see. Here.
X to the 8th. Or
Oh,
6. Are you
yeah, the 6. Yeah. All right, cool. Yeah. Oh, so even times even is even.
Okay.
And then for that matter, I mean, we might as well go through all cases. If you do like even times odd, so if we do like x squared times x cubed, what does that get you?
X to the 5th.
X to the 5th. So that gets you an odd function. And then odd times odd. So you could say like maybe x times x cubed or something. Those are both odd. What do you get when you do those?
X to the 4th.
X to the 4th. So odd times odd is even. Okay. Now, obviously, these aren't proofs, but they can help you remember in a pinch, right?
Yeah.
Yeah. Gosh, where's everybody gone? Okay. So then that means that for an, if f of x is even,
So
what?
then you could double it.
Yeah. All right. And then what about Bn if f of x is even?
That one's 0.
Yeah, that one's 0, right? Because if Bn, so if f of x happens to be even, sign is odd. Even times odd is odd. So, and if you integrate an odd function from minus L to L, you get 0. Okay, cool. And then, okay, so then if I'm going to do the f of x is even case, I might as well do the f of x is odd case. So there's one special case. So basically, if you have an even function, then your series doesn't have any signs in it because all of the b's are 0, right? So you basically, if f of x is even, then I get a series that just has cosines in it, or a Fourier cosine series. If f of x is odd, then what's a naught?
Zero.
Yeah, a naught would be 0, and then an. So and the original formula for it's up here. So if f of x is odd, we get odd times even.
So is it 0?
Yep. And then what's Bn if f of x happens to be an odd function?
You double it and go 0 to L.
Yeah. Perfect. Okay. So, yeah. So these are special cases worth keeping in mind. And in fact, all of that junk about like half range extensions and stuff like that is basically just this. It's just okay. You're given half of you're given half of the function, and you're just pretending whether it's even or odd, and so you're doing one of these. And the cool thing is you only have to know like the right half of it plus the fact that it has this particular kind of symmetry. Okay, so let's do an example. There aren't too many examples of this that are really ridiculous. So let's say, so an example. So let's say f of x is equal to, I don't know, 2 minus x on the interval 0 to 2, and repeats with a period of 2. Okay, so here's my f of x. So let's see here. So if I sketch what f of x might look like. So 2 minus x on the interval from 0 to 2 looks like that, right? And then this thing repeats itself over and over and over again. So, and then I guess there would be like another one over here, and so on and so on and so on. Dot, dot, dot to the left, dot, dot, dot to the right. Okay, so there's, do you know what actually there's a special name for this kind of wave. Do you know what this is called?
No.
It is called a sawtooth. Because if you look at this is one of those things that you could tell like engineers' names and not mathematicians, because it literally looks like if you zoomed in on a saw that you would cut wood with, it looks like the teeth of a saw. So yeah. Okay. So actually, so notice for this one, I gave you, there's a couple of things going on with this one. One, is this even or odd?
It's neither.
Yeah, this is neither even nor odd. So that's something to watch out for. Not every function is even or odd. There's many, many functions that are neither even nor odd. Although interestingly, you can split this up into an even part plus an odd part, but I don't think we want to do that. Okay, what's the L for this one? So the L that goes in all of those formulas.
1.
Yeah, so the period is 2. And so the L equals 1, so just like half the period. Okay. Now, if you notice, the original formulas that we had, like the bounds on the integral were from minus L to L. It doesn't have to be that way. So we could just make the limits of the integral just be 1 period. So instead of going, because I don't really particularly want to go from -1 to 1 for this, because then I'd have to split it up into 2 pieces, right? I could just as easily go from 0 to 2 and then leave everything else the same. Does that sort of make sense? So in general, so the regular formula that we have is, say for an, for an is like 1 over L integral from minus L to L f of x times cosine n pi over L x dx. Okay, we don't always have to go minus L to L. So basically, what matters about these limits of integration here are that they're 1 period apart. For symmetry purposes, a lot of times we like to do minus L to L, but it appears in this case, well, there isn't any symmetry. And if I do the 1 period from 0 to 2L, then that would be better. Does that make sense? So the limits of integration can just as easily be 0 to 2L. And then we just leave everything else in the formula the same. Okay. So for us, because we could say like, oh, the interval 0 to 2, that's like sort of our base period. That's 1 period. Or because that's where we have the function, right? That's, yeah, and I would rather not actually like figure out the equation of this line and then do the piecewise thing from -1 to 1. You know what I mean?
Mm-hmm.
Okay, so that's a little tricky bit for this one, but other than that, so that's the only thing we got to do. So basically, if we want to find the Fourier series for f of x, then basically what we got to do is, well, just plug into our formulas, right? So, well, we can rewrite this f of x as some constant plus the sum as n goes from 1 to infinity of some constants times cosine. So since the L was 1, it would be n pi over 1 x plus some other constants times sine of n pi over 1 x. And then we got to plug into those integral formulas with our slightly altered limits of integration here, but to figure out what the a's and b's are. So the a naught would be, so it's 1 over 2L, right? So it's 1 over 2. And then we're going to go 0 to 2 instead of -1 to 1 of our function, 2 minus x dx. Our an is going to be 1 over L, and then our integral is 0 to 2L of our f of x times cosine. n pi over L x dx. And then our Bn is going to be 1 over L integral from 0 to 2L 2 minus x. So that's our function sine n pi over 1 x dx. Okay, so we're just plugging straight into the formulas that I had on the previous page, right?
Mm-hmm.
And we're just, okay, so the rest is do these integrals, and then those are your A's and B's. And then once you've got your A's and B's, you plug them back into here, and that's your series. Okay, make sense?
Yeah.
Okay, so by the way, the A naught is 1. I have a super sneaky way of doing that without, well, I can't always do it. When it's straight lines, I can do it. The AN is 1 because, the A naught is 1 because the A naught is the average value of this. So like it's linearly decreasing from 2 to 0, and then it does that over and over and over again. So the average value is 1. So that's a fun shortcut if you can do it. You guys were sort of stuck with doing all of the integration by parts junk for AN and BN. You want to work through that?
We don't have to.
Okay.
But just do like u, sorry. 2 minus x is your u, and then the other one's your dv.
Yeah. So okay. So we could just say from this point on, evaluate the integrals and then plug the results back into the series, and then that's your answer. So evaluate these, plug the results back into the series. Cool. All right. So that's basically how that works. Right on. So again, last group, so we could go over anything you guys want. So what else do you guys want to see? Do you want to see more Fourier series stuff? Or you want to go backwards? You want to work some practice problems? What do you want to do?
Could we do one like a power series to solve an ODE?
Whoa, all right. That's going to be on the test?
Yeah.
Oh, okay. Yeah, those are gnarly. Okay. So using a power series to solve an ODE. Okay. Now, the principle behind this is actually really straightforward. It's just, it's a lot of work. So there's not really any getting around that. So let's see here. It's really hard to come up with one that's not like super difficult. All right. So let's say, I've got like y double prime plus, say, 3x y prime minus 4y equals 0. So I just like sort of made that up off the top of my head, and well, we'll find the general solution. Okay, so a little bit of ODE review. So this is a second order ODE. So actually, do you know what the O in ODE stands for? Because I don't know if you talked about that when you took Math 4B.
Ordinary.
Ordinary. Okay, what's ordinary about these? How come all of us, you took an entire class on these and you never called them ordinary? Why are they all of a sudden just ordinary differential equations?
I don't know.
Yeah, okay. So it's to distinguish them from partial differential equations. So they involve ordinary derivatives, right? So it's single variable functions, ordinary derivatives. So that's all. Okay, they're not necessarily easier or anything like that. Okay, so it's second order. and it's linear, and it's homogeneous. Okay, so so in general, the general solution to something like this is usually like a linear combination of two functions. Does that make sense?
Yeah.
So that it's usually like C1 times some function plus C2 times some other function, right?
Mm-hmm.
Okay, and so what we're basically going to assume is that we just assume that whatever our solution is, and is going to be or I guess another way of putting it, there will be two arbitrary constants that we would need initial conditions to figure out. So what we're going to do is we're just going to assume that whatever our y is, it has a power series. So assume that y can be represented by a power series centered at 0. So like a Maclaurin series, basically, right? So so in other words, we're just going to assume that y takes the general form. The sum as n goes from 0 to infinity of Cn times x to the n. And there's like little checks that you could do to make sure that you can assume this. So for instance, basically as long as you solve for y double prime and you don't get any like crazy singular points or whatever, then you're cool to do this. Now if we expand this, we get y equals like c0 plus c1 x plus c2 x squared plus c3 x cubed, etc. All right, so we're just assuming that whatever our function is, we can write it like that. And the idea is what we usually call as our arbitrary constants. So the c0 and c1 are the arbitrary constants. And then the rest of the coefficients, the C2, C3, C4, etc., those can be written in terms of C0 and C1. So the rest, so that would be like C2, C3, C4, etc., can be written in terms of C0 and C1. Okay. And so the idea is ultimately what our answer is going to look like, unless we have some initial conditions, is we're going to have, so the answer will look like this, or the solution. Y equals C0 times some stuff plus C1 times some junk. Okay, and it'll actually be C0 times 1 plus stuff and C plus C1 times X plus junk if you want to get more specific, but yeah. All right. So this is like big, broad overview of what we're doing here. All we're doing is we're just saying, all right, well, whatever function y or functions y solve this differential equation, we're just going to assume we can write it like this, and then hopefully we could use the differential equation to like relate all of the c's together. And as we'll see, we can do that pretty straightforwardly. So, all right, now it's a big mess with the sigma notation, so we got to be very, very careful with this stuff. So y double prime plus 2. All right, so I'm going to rewrite my differential equation right here. So it was y double prime plus 3x y prime minus 4y equals 0. And then, so our step 1 is we're just going to assume y is equal to n goes from 0 to infinity Cn x to the n. So we're just going to guess that whatever our function is, it has this form And I guess our goal is to figure out what all the C's are in terms of C0 and C1. Okay, so I guess the next step would be just like somehow substitute this into the differential equation, right? So we want to substitute our guess into the dE. So in order to do that, we need to compute two derivatives of y, right?
Right.
Okay, so y prime. So if I take the derivative of this junk, what do I get?
The sum from 1 to infinity of n times Cn x to the n minus 1.
Cool. Why is it suddenly going from 1 to infinity instead of 0 to infinity?
Because the 0 term is 0.
Yeah, yeah. Or you could say it goes away. Like here, the 0 term is a constant. The derivative of that is 0, so I don't really need to like keep it around. I guess this would work just as well if I kept it at n goes from 0, because that would be 0. So, but I think it's more polite to write it like this. All right, we need y double prime. So what's that?
The sum from 2 to infinity of n times n minus 1 Cn x to the n minus 2.
Okay, cool. And we want to plug all of this into that original differential equation, right? All right, so it's going to look a little bit messy at first, and we're going to spend a lot of time cleaning it up. All right, and that's like where, in my opinion, that's where like the bulk of the work of this is, and like there's a couple of like very subtle steps that we're going to take in there that hopefully like I'll slow down when we get to those parts. So we substitute in, so we get the y double prime, so that would be n goes from 2 to infinity of n times n minus 1 times Cn times x to the n minus 2, and then plus 3x times y prime. So here's y prime. What would happen if I took y prime and I just like multiplied it by x?
It would be x to the n.
Yeah, because it's just like add 1 to that exponent there. Okay, so cool. So I'll put the 3x on the inside. So this would be n goes from 1 to infinity. So this would be 3n, because that was where this 3 went, and then Cn, and then x to the n. Cool. And then minus 4y. Okay, so that would be minus n goes from 0 to infinity 4 Cn x to the n. And then that is all supposed to be equal to 0, right? Okay, so what on earth do we do with this mess? What's going on here?
We want the x's to all be to the same power.
Okay.
And to start at the same, like, and sum, like the sum to start at the same n value.
Yeah. Okay, so yes, all of that is true. So let's see here. There's a number of ways of doing this, by the way. So yeah, and the reason is basically we want to combine all of this into a single sum, and then basically have one sum and have that entire sum be junk times x to the n. Okay, so let's focus on making the exponents the same power first. So let's make all the exponents all How can we do that?
For the first one, you can say that it starts at 0 and then add 2 to every n.
Okay. Yeah, and then that way you would have an x to the n here.
Mm-hmm.
So we could say like oh man, it's hard to use the same symbol here, but like, so here's what I'm going to do. I'm going to say, so for this sum, I'm going to say my shiny new n, right, would be the same thing as, so there's like an n with a star on it, so it's all shiny, right? But then once we plug it in, it won't be shiny anymore. It will have, it will have driven off the lot and lost 50% of its value. So yeah, so my shiny new n is equal to my old n minus 2, which means my old n is the same thing as my shiny new n plus 2, right? So that means if my old n is 2, then my shiny new n would be 0. So n star goes from 0. And then, well, infinity minus 2 is infinity. And then, yeah, and then here I take all my old n's and replace them with my shiny new n plus 2. Okay, so then this would be n star plus 2 times n. So if it's n star plus 2 minus 1, that would be plus 1. And then times c, so shiny new n plus 2. And then again, I'll get rid of the shines on these. And then x to the shiny new n. All right. And then I guess what, leave the other two sums the same?
You can take out, oh,
I guess for this step, let's just leave the other two the same. So,
yeah.
so n goes from 1 to infinity of 3n cn. Don't want to do too many steps at a time here. Of 4cn x to the n equals 0. Okay, cool. Yeah, and then we could get rid of all the little stars on those because, like, okay, these things get old real fast, and then now everything's n. Okay. Okay, so now this middle term is the oddball, right? This one starts at n equals 1, and then this one starts at n equals 0. Or these other two start at n equals 0. So there's two ways to deal with this. So one, which is what I think you were about to suggest, is to just like remove the 0 terms from each of these guys, so they all start at 1.
Yeah.
And then just sort of like, okay, so deal with those. Another one, in this case, check it out. Well, I mean, this middle sum right here, we could just as well make it start at 0, right? And it wouldn't change anything, right? Because the n equals 0 term is just 0.
Yeah.
Okay, so, but either one of those will work. So I don't want to like say like one's better than the other. So I don't know, which one would you prefer? The removing terms or just changing this one to 0?
I mean, I've only ever done it the first way, so could we do it that
Oh,
change
sure.
it to 0?
Yeah, yeah, and you'll see we'll get the same results. It like, yeah, yeah. So this one could just as easy. So since if n was equal to 0, this would be 0. So this doesn't change if we start at n equals 0. So we basically just say like, well, okay, it'll be the same thing if this one's n goes from 0 to infinity, and then all right, well they're all this. They all go from 0 to infinity now. So then now, yeah, so now we could basically combine them and factor out the x to the n, right? So now this whole thing becomes the sum as n goes from 0 to infinity, and we're going to put in big brackets everything except for the x to the n. So this would be n plus 2 times n plus 1 times c sub n plus 2, and then plus 3n minus 4 times cn, all of that times x to the n is equal to 0. Okay, so double check my work here, make sure I did that okay. I think I did that all right.
Mm-hmm.
Okay. Yeah, so I just combined the 3n minus 4 times cn. All right. Okay, so this is what happens here. Basically, if we were to expand this, right, this would be some junk times x to the 0 plus some other junk times x to the 1 plus some other junk times x to the 2 plus some other junk times x to the 3, and so on and so on and so on. And then all of that is supposed to be equal to 0 no matter what x is. So basically, the only way for that to be true is if each of the individual coefficients is 0. Each of the stuff in the brackets is 0 if n is equal to 0 or 1 or 2 or 3 or 4. Okay, so basically what we could do is just set this thing equal to 0. And then that's our so-called recursion formula. So let's see. So our recursion formula, we just set the coefficients, the stuff in the brackets, equal to 0. And then if we solve for the Cn plus 2, that would be, well, 4 minus 3n divided by n plus 1 times n plus 2 times Cn. Okay. And then this recursion formula, we could use n equals 0, 1, 2, 3, etc. Okay. And then this is what we're going to do to generate all of our C's. We're going to use this sort of recursion formula here. And by the way, if I plug in n equals 0 into this, what you'll get is the same thing as if you just removed the constants from the first and third term here, and set them equal to 0.
Okay.
All right. So, all right, I need another page for this. So basically, we make a big long list, and usually, so if it's a test problem or a homework problem or whatever, it'll tell you to stop somewhere. Some of these are cleverly constructed so that after a while, the numerator might be 0, and so the rest of the terms are 0 after that. And so in that case, the solution might actually be like a polynomial. So, but let's see how this works. Okay, so let me rewrite the recursion formula here. So it's, what is it, 4 minus 3n over n plus 1 plus 2. Okay. So we got Cn plus 2 equals 4 minus 3n over n plus 1 times n plus 2 times Cn, right? And we use this to generate our C's, and basically we'll stop when we get tired. I don't think you're usually under any obligation to actually figure out the pattern here. There are a couple of special ones where you might have to, but usually it'll say like stop when you get to x to the 9th or something like that. Okay, so if I plug in n equals 0, what does this formula become?
C sub 2 equals 4 over 1 times 2 times C0.
Yeah, so I guess C2 is equal to 2C0.
Mm-hmm.
So we get C2 equals 2C0. Cool. Right on. And then, okay, and so by the way, if you would have removed the constant term or the n equals 0 terms out of the series, this is what you would have ended up with. So yeah, if I plug in n equals 1, what do we get?
C sub 3 equals 1 over 2 times 3 C sub 1.
Yeah, so we get C3 equals 1/6 C1. Okay, cool. I'll put that in a box, right? And we just keep going, right? So n equals 2. What is that going to give us?
C sub 4 equals -2 over 3 times 4 times c sub 2.
All right. And then, and now, of course, the c sub 2 was already 2 times c sub 0, right?
Yeah.
So we could substitute that in, right? So c sub 4 equals -2 over 3 times 4 times 2 c sub 0. And so I guess what's that? That simplifies down to -1/3 c0, I think.
Yeah.
Okay, cool. So that's, so c sub 4 equals -1/3 c sub 0. Okay. And then if I plug in n equals, where are we at? 3? So then what do we get?
C sub 5 equals -5.
Yes. Okay. -5 over
4 times 3. Wait. Yeah.
4 times 5? Yeah, because the n was 3, right?
Yeah.
Yeah, so 3 plus 1 is 4, 3 plus 2 is 5. Okay, cool. So, and then times c sub 3. Okay. So then, so the c sub 3 was just 1/6 c1, right? So, oh, times 1/6 c1. Haha. And then I guess, what is that? -1 over 24. So c5 -1 over 24 c1. So can you see how, like, ultimately all of the even terms are going to end up being like some number times c0, and then all of the odd terms, the way this is going, are going to end up being some number times c1. Okay, so just to make this look nicer, I'll do one more, or, well, I'll do one more of each, one more even, one more odd. So if I do n equals, it doesn't look like any of these are going to zero out, so we're going to have to stop somewhere. But if I do n equals 4, so let's see here. So that would be c6 equals, oh, lost my formula here. Here we go. C6 equals, so we're doing n equals 4, right? So that's -8 over 5 times 6, and then times C4, which was -1/3 C0. And so if we clean this up a little bit, it's positive, and then, oh, nothing cancels. It's just like 8 over 90 C0. And then if we do n equals 5, so we'll get 4 minus 15 is, so, oh, wait, hang on. So this would be C7 equals, and then 4 minus 15 is -11 over 6 times 7. And then times C5, but C5 was -1 over 24, C1. Oh man, I'm reaching my limits of multiplication in my head here. What the heck is, so it's positive. What the heck is 42 times 24? I mean, I suppose I could get out a calculator or whatever, but
1008.
1008. That's a good number. C1. Okay, cool. Now, we can keep going, right? And we'll just keep getting, if you notice these numbers are getting smaller, that's good. That means it probably converges. And they look to be getting smaller pretty rapidly. It's hard to tell. The odds seem to be decreasing faster than the evens, and they appear to be alternating and all of that stuff, and you can figure out properties of these things. But so here, this is what our results are though, right? So remember, our original guess was that our solution was going to be of the form y equals, so we went out to c0 plus c1x plus c2 x squared plus c3 x cubed plus c4 x to the fourth plus c5 x to the fifth plus c6 x to the sixth plus c7 x to the seventh plus yada yada yada, right? So that we're just, so this whole process started when we just guessed that whatever our solution was, it looked like this. So, and then what we got was, well, we can write all of the even terms as like some number as C0, and we can write all of the odd terms as some number times C1, and then the C0 and the C1 end up being just left as C0 and C1. So, okay, so then we get, so if we plug in all of our results here, right? So C0 stays C0, C1 stays C1. So Y is equal to C0 plus C1x, and then our C2 was 2C0, so plus 2C0 times x squared, and our C3 was, where was that? 1/6 C1, so we get plus 1/6 C1 x cubed, and then our C4 was minus 1/3 C0, so minus 1/3 C0 x to the fourth, and our C5 was, so we get minus 1/24 C1 x to the fifth, and then plus 8/90 C0 x to the sixth, and then plus, oh man, 11/1008 C1 times x to the seventh, plus, if I really need to, I can figure out more terms. You know, this is where I ran out of paper, basically. And so then we could group these into C0 times a bunch of junk and plus C1 times a bunch of junk. So when we do that, we get, so C0, so all the terms of C0, well, we got a 1 there. And then we got plus a 2x squared there. And then minus a 1/3 x to the fourth. And then plus 8/90 x to the sixth. And then we know it goes farther, so plus dot dot dot. So this is like a sort of partial sum of one of our solutions, I guess. And then we group all the C1s together. So we got a x there. And then we got a plus 1/6 x cubed. And then minus 1/24 x to the fifth. And then plus 11/1008 x to the seventh, plus whatever else comes later, which I can in principle figure out via the recursion formula. You know, yeah, and then this would be our general solution, or at least, I guess, part of our general solution, because we haven't worked out what's beyond the dot dot dots here. But it's at least like, you know, if we leave off the dot dot dots, it would be like a good approximation to a general solution. Whew. All right. Does that make sense?
Yeah.
All right. So by the way, initial conditions, the way they work here. So see if I can move this down a little bit. All right. So if I look at initial conditions, what's y of 0? Might actually be helpful to look at this version of it.
C0.
C0. Ah, okay. And then what's y prime of 0?
C1.
C1. Okay. So basically, so this could be written as that's like whatever y of 0 is times this chunk plus whatever y prime of 0 is times this chunk. Yeah. Often you're asked to like choose between one of these. So sometimes when you do this, like one of these ends up being like this just infinite series with a dot dot dot, and then the other one ends up being just a polynomial, like it just terminates. Um, Basically, if you can have a recursion formula up here, or if I twiddled with the numbers a little bit, I could come up with a recursion formula where it like just became n equals 0 after like I don't know, like after C7 and above or whatever. And so then I'd get like a 5th degree polynomial for the odds or something like that. So yeah. Um, yeah, okay, but that's how you do that. And that is a valid way of solving a differential equation. It's not in spirit any different than the way you might remember doing it in Math 4B, which was basically you guess your function is an exponential, and then that gives you a polynomial that you got to solve, and you find the roots of that polynomial, and that tells you your solution. In spirit, this is the same as that. We just guess that our function is a particular form, we plug it in, and then we see what we could say about the particular form. It's just there's more stuff to figure out with this one, that's all. All right, so yeah, so that's what that is. All right, so I would imagine that this, I mean, for a test like this would be about as difficult as one of those could get. I don't know, maybe, yeah, so you'd basically go down with something like this, and then they might give you initial conditions or whatever, and they'll probably tell you like where to stop.
I think we also have to do the series part of it, but
Oh, you have to actually spot the pattern?
yeah.
Oh, geez, that's a lot harder. Yeah, I don't particularly want to spot the series for this one. Well, because you have like a separate thing to do with the evens and the odds, right? So, okay, so in that case, it's probably better to write it as like the factorial chunk right here. I don't know, I could try it with this one. So let's say I tried it with the even ones. Let's see. All right, no guarantees I'm going to actually be able to do this, by the way. So we'll see. But I'll see how good my pattern recognition skills are. All right, so we had our Cn was 4 minus 3n over n plus 1 times n plus 2, right? Okay, and so I just want to look at the even ones. So for the even terms, so if we just say like, so for the evens, the C2 was 2C0. The C4, so let's plug in n equals 2, right? So the C4 was,
Isn't it Cn plus 2 equals that?
oh, Cn plus 2 equals this times Cn. Thank you. All right. Sorry, I was in too much of a rush. All right. Yeah, so and then C4 is, so that's we're plugging n equals 2 into there, right? So that's 4 minus 3 times negative, what is that, negative 2
Mhm.
over
3 times 4.
3 times 4. And then times 2C0. Okay, right? All right, so if I'm looking for a pattern, I'm just going to leave it like this.
Yeah.
C6 would be negative, so this would be plugging in n equals 4 into here, right? So this is negative 8 over 5 times 6
Mm-hmm.
times this stuff times negative 2 over 3 times 4, okay, times 2 C naught. Okay, so this denominator here is starting to look a bit Like a factorial missing the 2?
Yeah.
Okay. And then we just got to figure out what the heck is going on with the numerator. So the numerator, ooh, that's going to be nasty. But like, so yeah, so I could put an extra 2 on the bottom and an extra 2 on the top, and that'll give me like an n factorial, right? So by the way, since these are evens, these will be c sub 2n. Does that make sense?
Yeah.
So far, so I've got like so it'd be a 2n factorial, right? Because there's like 6 factors. So if 2n is 6, right? And then I've got, but then I've also got like a 2 up here because I'm missing the 2. All right. And then, all right, I'm also going to have as alternating doodad, right? And it appears like the alternating doodad, like it appears the pattern starts not with C0, maybe like an alternate, it might start after 1 or something like that. So we'll have an alternating. So if n is 3, so we'll have like a -1 to the n plus 1. And then I just got to figure out what all of these guys are, right? So here we'll have like we have a 2 times a 2 times an 8. So what's left? We got like 2 times 2 times 8 times da 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 da, right? And so we want to figure out the pattern for this junk. So we got like a 2 times 2 times 8. I took out the negative out of this. And so, and then this would be, so 3n minus 4 times dot 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 times 3n minus 4. I don't know if there's a good way to write that. So I think it starts here, right? Because the n skips by 2, right? So I guess the first thing here is rewrite this as something like 2n. 2 times 8 times, so it'd be 3 halves times 2n. And then minus 4. I mean, I guess you could write it like that, or you could say like that's what the numerator would be. So C2. So you could just say like C2n would be 2 times 2 times 8 times da 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 times 3n minus 4, and then times we got, and then times this junk right here times the 2 times -1 to the n plus 1 over 2n factorial, and then times C0. So I think sometimes you might have to just write it as a dot dot dot. That's the thing, is there are notations for this where you can remove the dot dot dot. There's stuff called like falling factorials that you can use, but I don't know, you guys didn't learn any of that, so I wouldn't worry about that. I think for this particular one, this is probably about as good as I can get.
Okay.
Yeah. All right. I guess we don't have that much time left. Do you guys have any other quick things that you want to see?
Like, so for some of these, when we do the Fourier series, we have to like find some identity at the end, like on our practice problems. So do you have like a quick list of like the known ones?
So are you talking about like evaluating a sum, or are you talking about
Like pi and pi squared over,
oh yeah. So those basically what happens with those is you find your Fourier series, and then it'll tell you you can use this series to compute such and such a sum. Usually what ends up happening is you just plug in a specific x value and then sort of simplify. And so once you've computed your Fourier series, you just plug in an easy x value, and so that easy x value is either 0 or like half the period or something like that.
Mm-hmm.
And then you clean it up a little bit, and then you can use that to figure out your desired sum.
Okay.
Yeah, so I don't have an example off the top of my head where I like know the Fourier series, but like yeah, but yeah, that's usually the way you do it with pi squared over 6. Or did you guys learn Parseval's identity?
Not specifically.
That sounds like a no. Okay, so cool. So then forget I said that. And okay, yeah. So basically, you find a Fourier series, and then like the follow-up question will be use this or compute this sum, right? Like it would be really mean to like ask you to compute the sum without having, giving you the prompt to compute the Fourier series that can give you that sum. So yeah, and it basically usually boils down to either plugging in x equals 0. So say if it's a period of 2 pi, you'd either plug in x equals 0 or x equals pi over 2, or maybe x equals pi.
You know, like the 1 plus 1 over n to the n equals e thing.
The 1 plus, oh yeah, this limit, right? So limit as n approaches infinity of 1 plus 1 over n raised to the n. That's e.
Yeah. Is there any other like identities like that?
I guess the full general version of this is limit as n approaches infinity of 1 plus x to over n to the n. That's e to the x. So like this is just the special case when x is 1, but like if x was -1, you get like a 1 minus 1 over n to the n. That gives you e to the -1, stuff like that. And actually this n could be like n plus a constant. It would still be the same. So if you had like limit as n approaches infinity of 1 plus x over n plus a, where a is just some number raised to the n, that's also e to the x. And then I guess another one that's useful for the root test is the limit as n approaches infinity of n to the 1 over n is equal to 1. And in fact, even better, limit as n approaches infinity of n to like the p over n, where p is literally any number, that's also 1. And you could use the same sort of like log arguments in order to prove this, but like that's, yeah. So that way if you do like the root test where you've got like some polynomial thingy, and in fact, actually here, so the limit as n approaches infinity of poly of n, where n, that just means some polynomial in n raised to the 1 over n, that's 1. Okay, this is probably the most general way of writing that. So these are useful if you're using like the root test, I think. Yeah. Yeah, off the top of my head, like I think like these are probably the most immediately useful because it's just like it does take a while to actually compute these, and so if you and these are like sort of known definitions for the e and e to the x and all of that stuff. So cool. So I think what I will do is Chen, if you didn't hear, I'll extend my my drop-in hours to be a little bit longer tomorrow to make up for no group, and I can go over practice problems. I can go over whatever questions you guys got, and I'll also maybe tomorrow as well. I'll post an additional thing on like some more Fourier series stuff, and then go to my website and check out practice test. So yeah. All right. All right. I think I can